Okay, so in the previous video we actually talked about mainly on the S domain stuff, how to find your hidden zeros. Now we're gonna find now we're gonna discuss with you how to transform the S domain into the digital system. Alright, what do we do? So therefore I'll just copy this one and I'm just gonna paste it all over here. Okay, so let's just start it out. Okay, the first step that I need to do for this case, after I know that I requires one more zero, right? Because I think you straight away know already, right? Right? It's because S plus infinity. Okay, it's because the order over here is one order larger than this. So the order of pole minus order of 0, right? This is 2 minus 1 is equals to 1. So this tells you that the number of zeros you need. So therefore over here I need one more. So therefore this is just the meaning of that. Okay? So next what we're gonna do is actually to redefine this whole transfer function. Okay? I'm gonna give you this understanding of S plus A for any A is equals to S minus A. Alright? So I just repeat again, S plus A, I write it as S minus A. So minus A is still S plus A lah. I just need to rewrite at this form. Okay? So this A can be any A. So for example, if it's S plus 2, I'll just write it as S minus 2. Okay, if it's S plus infinity, alright, I'll just write it as S minus infinity. Okay? And then if it's for the bottom one, now this is all the whatever stuff that you want. I'll just write it as so their roots is actually S plus 3 and S plus 1. Okay, if you multiply you'll get this thing lah. So I'll just simply rewrite them as S minus 3, which is this one, okay, multiplied by S minus 1, which is this one. Okay, then I'll just erase this. Okay, so the first step is someone to rewrite whatever thing over as the sign. Okay. Nonetheless, if you have a conjugate, for example S squared plus S plus 1, if you were to write in terms of minus form, alright, the coefficients are all 1. So I'll just rewrite as minus 1 plus minus, alright, and then 1 minus 4 divided by 2. I'm just simply trying to find the roots of your S squared plus S plus 1. Okay. I'll have minus half plus minus great job, 3 over square root 3 over 2. Okay, so the roots is minus half plus j square root 3 over 2, or minus half minus j square root over 2. So if you were to write it out in this case, then you have S minus, alright, now this whole thing is, maybe I should rewrite as this form, minus half plus this thing, or minus half minus this thing. So over here this is minus half plus this thing. So because this is now, if you were to have the roots, normally you just write it as S plus and then you just sub it in only, right? You just happy put it in. Okay, so therefore don't do that, because you're gonna write it in terms of S minus. So if you were to change it to S minus, so I have, instead of minus over here I have a plus, right? So this one is, instead of plus I have minus. Okay, I have something like this. So if I were to work it out, I will just multiply in the minus again, just to show you. I have S, alright. If I were to factorize out them, anyway, if I were to multiply it in, I'll have S minus half plus j square root 3 over 2. Okay, so to speak lah. Alright, which is the same as this one. Haven't that if I were to bracket them lah. Okay. Sorry, this one is no. I should have factorized them out. Okay, so this thing over here can be written as this one. I just want to prove to you that this thing is equals to this thing, is that I will factorize out the negative sign. So if I have to factorize a negative sign, I'll have S minus, this thing will become minus half plus j square root 3 over 2. Alright, which is this whole thing over here is this one. Okay, and then this minus and minus will add up together. You have S plus minus half plus j square root 3 over 2. which is initially this part over here. Okay, so I go through all this is just to prove to you that whenever you do a complex number, please take note that if you have a complex roots, for example minus half plus this thing, you're gonna change their sign. From minus you change to plus, from plus you change to minus, and just sub it into this thing, where your s minus something something something. I hope you kind of get what I mean. If you don't get what I mean, if you feel a bit unsure, click back a few minutes ago and watch again. Alright, please. This is pretty important for the complex roots. Alright, so please take note of that. Okay, so I've finished the complex understanding. So let's continue after we go through all this, but we are still looking at changing s plus a to s minus minus a type of style. Alright, where this thing over here can be normal roots, can be also complex numbers, so be very careful of that. Alright, the next thing I need to do is to define the second thing, which is z is equals to e minus at. Okay, there will be some confusion, alright, because this thing over here is for this case s plus a. Alright, so if you have minus a over here, you just write as minus a straight away. Okay, no need to change anything. But if you have a s plus a, because s plus a equals to s minus minus a, so the conversion is a little bit blurry, but so take note of this blurry part lah. But anyway, the definition is z equals to e minus at. Okay, so for all the s, all this s over here, just change it straight away to z. Okay, while the minus 2, right, this is your a, or you can say that this is minus a, you can straight away sub in all over here. Okay, so in this case I'll just write as minus e minus 2t. Okay, so over here this is minus 2, I'll just write as e minus 2t bracket, and over here s I'll just straight away write as z. I should define that z is equals to s also. Okay, so therefore minus this thing over here, I'll just write as e minus infinity t. That's all, that's straight away sub in only. Alright, and then divided by s, I change to z also, right? So I'll just have z minus, alright, e minus 3t. This is minus 3, I'll just write as e minus 3t. That's all. Same thing over here, the s, I'll just switch it to z. Okay, so I have z minus e minus t, because minus 1 is just 1. Minus 1 times t is still minus 1. Minus t. Okay, so I think you have somewhat understand what I mean. So if you don't understand, click back a few minutes ago also. The next thing you need to know is that your e minus infinity t is equals to negative 1. Okay, so if you were to write it in terms of the Eulers, alright, this thing over here is your Eulers, so to speak lah, okay? Actually not Eulers lah, sorry, my fault. Because this is not in terms of e minus j theta, I need a j. Over here there's no j. But anyway, even with that understanding, we can't prove to you anything. But I just want to let you know that if you have a e minus infinity t is equals to negative 1. Although this shouldn't be negative 1, because if you just type in into calculator e to the minus 111111111, you are just eventually equals to 0. But I don't know why to some extent they actually write it as okay. Actually no need to I also don't know. But anyway, if your s, for example, in the s domain is minus infinity, which is all the way at the back, right? Minus infinity. Okay, so if you remember in your this is s domain, this is z domain. So over here at the origin, where's the origin? Or the origin over here is being plotted over at this side, where the unit circle over here is 1. If you still remember, it's plotted at this particular point. Okay, then the further you go towards infinity, the further you go towards the origin. Right, this is for the real part lah. Okay, this is for the real part, because the real is minus infinity, it will go to this point. For the imaginary part that is going to infinity, or that is going towards infinity, okay, there is in fact no meaning. It's because you are looping around. If you still remember the imaginary, for this point is being plotted over here, for this point is being plotted over here, for this point is being plotted over here. You'll loop around this circle. You'll keep on looping and looping and looping around this circle, if you still remember for the definitions of our imaginary. Okay, so therefore if you keep on looping either -1 or 1, either -1 or 1, so therefore over here if it's imaginary towards infinity, normally they just write it as -1 because it can be -1 or it can be 1 for the z domain. Although when we straight away derive through this meaning, we can't get any stuff. Alright, but if you were to go into the understanding, or then things will be a little bit different. But there's many ways to explain. You can also explain the Euler's formula. Now I think of it, I think can. Alright, but I'll not go through the details. But at least you just need to memorize that e to the power minus infinity is equal to -1. Okay, by the definitions that I just told you, I think it's pretty much helpful already to give you the brief understanding of why do we choose -1. Okay, because it's just random. It can be -1, can be 1 also. Alright, it depends on whether which one you want to look at, things like that. But normally they choose as -1 right, because +1 is simply coming back to the origin. If you remember this thing, unit circle, this +1 is your origin at your S domain. This is Z domain. So definitely you can't put it as +1. You need, so if the further you go for the frequency in the imaginary, then the furthest you can go is -1 by the period, because this thing will keep on looping around. Right, to infinity you will loop around many circles. You will not go out of this thing. Okay, things like that. But anyway, let's just continue because we have like going into sidetrack a lot already. So we can simply write this term over here as -1. Okay, so therefore I'll just copy this thing. I'll just paste. So I'll just switch it as this thing over here. I'll erase it. I'll replace it as -1. Okay. Yeah, because -1 minus -1 is equals to +1, so I have z plus 1. Okay. So over here, this is your final stuff. This is the representation. This equation is a representation of your this thing over here. Okay, they are equivalent now. Okay, they're equals to each other. Okay. I can't prove to you, but just take it lah, because this is coming from my teacher. So by comparison, you can somewhat see the same thing. This thing over here is equals to this one. This thing over here is equals to this one. This thing over here and this thing over here, both of them is equals to this whole chunk over here. Okay. So so at the end of the day, I just want you to take note of 5 things. The first one is s plus a, you change it to s minus a. The second thing is z is equals to e minus at. Alright, that's all I just want you to know. You can straight away write this thing as e minus at. So I repeat again, you can straight away write this one as e minus at, and this s you can change to z, because s is equals to z ma. Alright, I think you get what I mean, because for example s minus -2, I can straight away write, I know that s is equals to z, I just write z minus, I know that -2 can be straight away as e minus 2t. Bam, that's it, finish, bang bang. Okay, so that's all. And then next is e minus infinity t is equals to -1 by the unit circle type of explanations. Just it's somewhere over here. Alright, in the S domain you go to infinity imaginary. Alright, you just keep on looping around. Alright, but the furthest you can go is -1 from the +1 region, so to speak. Alright, and the last one is not defined here, is that your z plus 1 is the equivalent of your s plus infinity. Okay, so whenever, so if you know that you need to require one more zero, straight away you know that in the z domain you will need to have a z plus 1. If you have 2 more zeros, which is square, you have a z plus 1 square. If you have 3 more zeros, then you have z plus 1 cube. Things like that. Alright? Not to be confused that In this case, we only have 1 0 lah. Okay, so therefore I have one more zeros in the z domain also, which is z plus 1. This is s plus infinity. So everything, the equivalent of s plus infinity is your z plus 1 in your z domain. Alright, so these are the 5 things that I think will be fairly useful for you to know. And the next video we'll do another example to actually strengthen your understanding. See you there.